Hey Perry, you're muted.
Okay. I had a little warm up on that. Can you hear me now? Yep, looks like it. Okay. So last week we started talking about temporal population models. And we talked about intrinsic growth rate, finite rate of population change, how those are directly linked, how those fit into the exponential model and how we can derive those from the exponential model, and how we can derive them directly from the BIDE model if we assume no immigration or emigration. So now today we're going to extend the exponential growth model to account for density dependence. And what I mean by density dependence is that birth rates, the intrinsic birth rates and the intrinsic death rates are going to decrease for birth rates and increase for death rates as the population size increases. So when we talk about the exponential growth model, let's see, I have to switch to my whiteboard here. When we talk about the exponential growth rate, we assumed, this assumption is implicit in the model, and it may not be obvious. We did talk about it in our assumptions, but we talked about our birth rates, which we called little b, and our death rates, which we called little d. And remember, b, we talked about total number of births equals little b times n in year t, and this is the rate, the per individual number of births in the population. And then for deaths, we have d equals little d times n. So now we're talking about this little b on the y-axis and this little d on the x-axis. With our exponential growth model, we assumed that this didn't change no matter what the population size was. So if we put population size on the x-axis, we assume that the birth rates stayed the same no matter whether the population was small or large. Same with death rates, that there is one fixed birth rate and death rate, and that was independent of how big the population size was. That's the assumption in the exponential growth model. Now, we can think about extending this, making this model more flexible in the exact same way we make our null model more flexible and allow it to change with a covariate. So we saw graphs that looked like this for our null model, where we have some covariate on the x-axis, and then we had like a detection probability or a survival probability on the y-axis here. And in our null model, if it was constant, we just had the same model. It didn't change with the covariate. So the exponential growth model is like a null model for population change, where we assume birth rates and death rates are constant and they don't change with population size. A logical extension to that, the next logical extension to that model, is to assume that as population size increases, birth rate decreases. So let's make this blue here. So as population size increase, birth rate is going to decrease. Or maybe it starts off at this intercept here and decreases. And as population size increases, death rate is going to increase. And the assumptions behind these are if there's more animals in the population, they're competing for resources, and therefore there's going to be less energy to go around to store and give towards reproduction in terms of our birth rates. And also, after animals are born, there's less resources available due to a lot of other animals out there, and therefore more are going to starve, so the death rate is going to increase. And the simplest way to extend the null model, where we have a flat value for all population size, is to make a linear relationship, a straight line relationship, just like we did with linear regression. Well, it turns out when we do this, this is the assumption that leads an exponential model into a logistic regression model. This is the math behind how an exponential model goes from an exponential model to a logistic regression model. All we're doing is changing the birth rate and the death rate to be a straight line with a slope and an intercept, a non-zero slope for both birth and death. That's the connection between logistic regression and exponential regression. So essentially, yep.
Sorry, can you make me co-host? There are apparently people in the waiting room.
Yeah. Good thing this is being recorded. All right. So where are you at? I don't even see you on here now.